Today we have a speaker from our own faculty, Andrey Rogachev. He came here 6 years ago, 2006, from the University of Illinois. He was there a postdoc for a few years. And actually, he got PhD in Japan. And so he came to the United States via Kapchuk. It's Bering to Alaska. Kapchuk is under Siberia. Chukotka. And so he will tell us today about the main project in his group, which is superconductors, insulator transition with one-dimension nanowires. But he has all kinds of other subjects to talk about. With Grace. Thank you.
So basically, my understanding is, first of all, I think before, and this is kind of a review work that I think intended to summarize the review. Yes, and it was designed sort of for this way. So my main plan for this talk is actually start from basically a review of what we are doing and how our group is sort of positioning ourselves. What is our goal? What we want to study? What we want to grow. So that's includes these several areas: quantum transport and kind of technical topics for quantum fabrication, advanced transport management, and so on. But then, in the second part of the fourth part of the talk, we'll come to sort of what was the main topic of our research, of what the kind of main problem that we are trying to address. And that is the problem of superconducting transitions, particularly in nanowires, but also we studied a little bit of this effect in two-dimensional. So here we are. So our group, if you ask me how we name our group, I would put the title quantum transport. So basically, by quantum, of course, if you take, for example, a piece of silicon of 1 cubic centimeter, of course, transport in this material is done by quantum mechanics. But here, by quantum, I mean something else. So if you have a system, then at some point, if, for example, you change the size of the system will start to behave as some kind of small quantum mechanical system. So for example, if you take a very small crystal, and then you have level quantization, and then the small crystal behaves as artificial atom. If you have a small transistor composed of small grain, then the transfer of the electron between this, let's call them source and drain, depends on capacitance of the system. Capacitance can be so small that the effect of charge discreteness is going to be important. Or for example, you may decrease the size of the system to such a state that certain inelastic length of inelastic scattering becomes larger than the size of the system, then you have spectacular manifestation of some kind of coherent behavior in the system. And transfer here actually stays for basically our main tool. So far, our main tool to draw this object was through the transport mechanics. From what I said, on technical side, that means that if we want to study quantum transport in this regard, we need to have two things. We need to have some tools to make very small systems. And very often, the other way around is actually to reduce temperature, because if you reduce temperature, then certain length actually becomes larger with smaller temperature. For example, inelastic scattering time becomes actually increases with decreasing temperature. So those the things are that we need to develop to address this field. We need to develop some kind of nanofabrication procedures, and we need to develop low temperature and we also need low noise technique. And the other thing that is sort of not necessary for this research, but something that I sort of would like to develop, and probably it's not to develop, is methods that are used to probe dynamics of the system, kind of dynamical methods. So having these methods, nanofabrication methods, and kind of dynamical, real-time dynamical tool, sort of opens up some opportunities for collaborative projects. And as far as collaborative projects are concerned, we're sort of not limited to this quantum transport core of our interest. And in fact, we initiated several collaborative projects, for example, with Professor Jarov, and also we will tell about that, and some projects related to the dynamic studies of organic alternating dyes, and that is a part of my kind of C grant. Having these opportunities also helps us to incorporate undergraduate students in our research, and actually in the past, I think I started doing this maybe 2.5 and 3 years ago. I had a number of undergraduate students working in my lab, and they actually mostly were involved in this sort of area of fast dynamic transfer of some organic materials. For example, Kevin Davenport, his project was to study, it still is in fact, to study high frequency behavior of single crystal organic field effect transistors. Dieter Biemans and Kevin actually does his Europe Fellowship in spring 2012. Dieter Biemans was also a student, and now he actually at the Sept Institution of Oceanography, and basically he was in charge of developing cross-correlation technique for noise spectroscopy. Again, kind of aimed for this project. There is Strasser, now is working on developing some kind of temperature cryostat for the same sort of measurement. James Kabornik, Jordan Brown also graduated, and he was developing this cryostat. And James, who joined my group, I think the latest, but he really involved in this kind of core activities. And in particular, he is now in charge of studies this cross-sectional effect on nanowire critical temperature, and this important topic of magnetic tune superconductor-insulator transition. In fact, James traveled with me to Ames National Lab, where we tried to implement these measurements in ours. So let me give you some hints of basically what is going on with these collaborative projects and what expertise in fact we have in terms of nanofabrication and dynamic quantum measurements. So here is a project that we initiated with Professor Ilya Zharov from chemistry, and his expertise is in fact related to some sort of creating responsive nanopore arrays. So far what he was doing, I mean, he did many things, but one of the examples here is array of, I think, spherical particles, and if the surface of these spherical particles is modified with some kind of organic molecules, then the transport, and here by transport I mean like it's actually everything is immersed in a liquid, so it's kind of transport of certain molecules in liquid through this membrane. So basically, the transport of these molecules is actually affected by surface modification of these molecules. So that's opposite. So our collaborative project actually utilizes our basically expertise in fabrication of these nanopore arrays. Basically, what is shown here is a silicon nitride membrane with a thickness of about, I think, 40 and 100 nanometers, and using electron-beam lithography, we create an array of the holes in this membrane. And then this membrane can separate the chambers and be filled with liquid, and then we may control the flow of this molecule through this array using one of the methods that Ilya developed. For example, you can actually modify the surface of this nanopore with some active molecules and basically affect the transport. And that is some preliminary tests were actually quite successful in this regard. But another interesting thing that we have not yet tried, but it's still possible, is actually to implement some kind of molecule transistor, in the sense that each nanopore here can be, well, all of them can be surrounded by some kind of metal gate, isolated, and then by applying potential to this gate, you may create some sort of molecule transistor. You may block flow of the ions through the system or let them pass, depending on what potential is there. So that is ongoing project with chemistry, and there is a kind of more developed project that is done in collaboration with a group of Vali Bardini, and here we try to study the effect of basically dynamics of carriers in organic lightweight dyes, and it's related to this so-called bombard effect. It was mentioned, I think, many times in this auditorium that bombard effect essentially occurs in lightweight dyes that have this structure. There is no magnetic materials in this device, but yet when we place no magnetic field, light output and current through the device responses typically enhances in this way. So what we contributed to this story? Basically, we developed a special technique that allows us to test impedance or admittance of this system. So basically, in addition to just DC sources typically applied to the system, we applied AC excitation, and as a result, we determined this quantity called admittance, and we plot frequency response for the system. And basically, it's a simple tool, but it allows you actually to test what relaxational processes you have in the system. What is, for example, transient time of impedance. And here there are some highlights of what we observed. So basically, admittance is characterized by two quantities. One of them is conductance, and another is capacitance. And what is shown here is a dependence on conductance as a function of frequency, and in fact we can quite accurately fit it with several relaxational processes, in particular this bump, I think originates from some kind of generational combination in this material. Cutoff here is due to the fact that you have shortage is so-called repolarization of permanent dipoles. One of the outcomes of this work is in fact that Omar effect, even though it has this cutoff here, this cutoff itself is extrinsic. It's not really related to Omar effect itself. We also have
I'm not sure I understood what you just said. The conductance is going way down to high frequency. And can you just repeat exactly what we said the reason for that is?
So, first of all, I'm going to give more detailed description of this project once the project is, and that's not the second, where everything will be explained in more detail. So, but here, statement is that this cutoff is not, it's extrinsic, because this other process not related to, basically to charge carriers in the system. So you have permanent dipoles, and if you excite them with electrical field, they start to do some kind of repolarization, and this gives you contribution to this effect, and this in fact shorts. Basically, that dominates your conductance at high frequency, and that's what gives you actually this structure. Okay, and there is everything is at room temperature. So another thing here is basically we have the second part, and this is just capacitance. And interesting about capacitance that actually we see it's negative. We have two contributions. One of them appears here, another kind of appears at low frequencies, and we think we understand now what's there coming from. And in particular here, I'm not going to give you explanation. In fact, I don't have a good explanation, but this is just, in my view, very nice remarkable effect by itself. What we found is that if we bias our device to a certain point, then we can actually, by applying a magnetic field, we can flip capacitance at low frequency from diversion negative to diversion positive. Being interesting effect, more details about that. So the other technique that we kind of developed in this Sept project is determining the noise, basically kind of developing the method to actually measure noise in these devices. And to do that, we actually had to develop this method, which is basically based on the fault that is our device, and biasing in this way is actually allowed to flow current through these two amplifiers, and in the essence, the goal of the technique is to reject or eliminate noise that is coming from these two amplifiers. So basically, the only thing that we are detecting is the noise from our organic light-emitting diodes itself. And those are some noise spectrums for typical samples that we have. And what we see here is actually quite interesting behavior. So basically, data apparently dominated by one over F contribution, and at low frequencies there is no effect of magnetic field, but at this intermediate frequency, what we see is a kind of bump. And looking at the literature, typically this bump, this upturn here, is associated with a specific contribution that is called generation recombination noise. This is noise that is coming. This is light emitting dyes. And basically, light emission occurs as a result of recombination of poles and helicals that are injected from the helicals. And there is a noise signal associated with this process. And what we see that this particular signal is actually affected, enhanced by climate. So this work is in progress. We not yet developed any model.
Why is the noise increasing from 10 to the 30?
That is, let's call it, we eliminate some effects related to this amplifiers, but not completely. I should say this is expected. So that is some noise. I guess it's from voltage noise of this amplifier when it goes is sort of picked up by the other. But that is expected, and I hope we can eliminate them when we find this data. Alright, so that is several examples of what we are doing as collaborative projects are concerned. But our main goal, and of course the main goal for this is to study superconductor-insulator transition in 1- and 2-dimensional systems. And that is one of the unresolved problem in classical complex matter physics. So why call it classical? Well, first of all, superconductivity, as you may know, is an area that is not short of supplying really hard problem for physical techniques. So basically, ECS theory, it took 50 years, actually, more than 50 years to develop ECS theory before experimental discovery of superconductivity. And now we have this phenomenon of high temperature superconductivity that was discovered in 1986, and yet people have not agreed what is the mechanism of this phenomenon. I put here classical because we are not really concerned with these new superconductors and their mechanisms. So materials that we are studying here are classical BCS or superconductors or materials in which superconductivity occurs as a result of electron-phonon coupling. Basically, electrons are coupled by interaction mediated by phons. And so basically, this BCS theory belongs in my classification to classical condensed matter physics, but still there is this problem of what is going on if you try to basically kill superconductivity in the system. So within BCS, pairing occurs as a result of this photon-mediated interaction between the states that have time reversal C. In a simple plane wave basis, this is just the states that have opposite spins and opposite momentum. So our gap itself depends on the correction parameter density of states. We can define basically what is the temperature, critical temperature of the system. So as I said, the question that I put on the top of my slide is actually related to this more general question of what is going on to superconductivity if size of the system is getting smaller. And there is actually several layers, several approaches, approximation of how we answer this question. In fact, in first approximation, the answer is, well, nothing really happens. If your system is clean and if you decrease its size, nothing really happens to superconductivity. And there is these beautiful results in which beautiful experiments in which aluminum grains are really decreased down to the size when level quantization becomes important, and only then when level quantization becomes comparable to superconducting gap, only then superconductivity started to basically decay. But that's already, it's probably not a piece of metal, but some kind of artificial metal. And in fact, historically, there was many studies of superconducting fields, but only recently, I think only in the last decade, very perfect superconducting fields were experimentally tested. And these experiments, in fact, confirmed what I just said. Reduction of the size of the system doesn't really do much to superconductivity if it's clean. What is shown here is basically, on the left side, we see some scanning type microscope. Well, I think images of some lab films that perfectly perfectly crystalline and deposited on some silicon atom. And if they're perfect, and this is confirmed by this other measurements where individual atoms are resolved, their critical temperature does not really change with the number of monolayers. It's kind of spectacular because the thickness is decreased down to 3 monolayers, and yet critical temperature stays the same. And only below these numbers, it starts to change. But at this point, it's already not clear. Is it really lab or some kind of other material? So basically, the statement is that...
Sorry, is there a lattice mismatch with the silicon?
I see. But at least it's perfectly crystalline. There is no disordered resources. So that is...
Do you know if they looked at the superfluid density or TC only?
I think they looked at the gap. Look at the gap. So it just was kind of STM measurements.
In principle, if you're talking about how good of a superconductor is, it's superfluid density that you need to look at, not TC.
Oh, but still, it's quite unexpected. Well, in general.
Right.
So that's, I think, what we have. Now, the things are changing when we add a little disorder to the system. And again, there is kind of 2 levels of what happens to the system when we have a disorder. In first approximation, basically, the statement is there is nothing really happens to the system. So basically, it means there is Anderson theorem that basically is saying, okay, if you have clean superconductor, you have plane waves, time reverse plane waves that do the plan. If you have disordered superconductor, you may still create 2 time reverse states, and now current happens between these 2 states, but otherwise, nothing really happens to the mechanism of BCS conduction. However, disorder itself, besides these things, it introduces several different things to the system that are going to be important and, in fact, detrimental to the disappearance of superconductors. First of all, of course, in real system, in real superconductor, in addition to this photon-mediating coupling, we have repulsion between electrons, they are charged particles. And if you introduce this disorder to a system, it effectively increases repulsion between electrons. As a reason for that, if you have clean system, wave packets for electrons are very spread. If you have disordered systems, they are more compact. So electrons actually feel each other much stronger. So phenomenologically, that can be introduced by, that can be kind of introduced to the system by adding this new star coefficient that is responsible for electron-electron repulsion. And disorder effectively increases this mechanism. So the theory, well, expectation is that your gap and your order parameter decreases uniformly as a result of increased disorder, and this mechanism is typically referred to as fermionic mechanism of suppression of superconductor. But in addition to that, disorder may do kind of tricky thing to your system. Basically, you may have homogeneously disordered state structurally, but yet superconductivity emerges as some kind of inhomogeneous state. There is numerical, or basically, simulation of the system, and the superconductivity occurs as these clusters that eventually are going to form basically percolation paths for the system. There is a twist in this theory, in this picture, in which it says that, well, in fact, these superconducting clusters has a form of fractals that penetrate each other, but it's more or less similar to that. So now, if you have this disorder-induced inhomogeneous state, the question is how superconducting, global superconducting state actually emerges out of that. So to do that, we need to some kind of coherent coupling between these two piles. And there is a number of theories that actually telling you how this coherent coupling can be destroyed or can be created. So there is like a model in which the coupling is related to this competition between long. Basically, to do the coupling, we need to transfer Cooper wave from one element to the other. There is charging energy related to that. So So electrons actually want to stay in different ions. But there is also a Josephson coupling between these two grains. So actually two grains want to share these two grains. And depending on these two parameters, you may get superconductor or insulator. So there is another picture which involves basically the presence of resistance between these two guys, and then you have this equation. So there is this Cooper-pair Borges duality picture in which Cooper-pair tunneling between ions is accompanied by motion of the vortex. And you have, if you have duality between these two things, then you have that basically an essence of this process. So there is many different models that are related to some materials, but as far as physics of two-dimensional systems is concerned, well, at least we have superconducting transition. So there is, if you take a field, disordered field, for example, here experiment is done on amorphous viscous, and if you change the thickness of the field, which effectively translated to disorder, for thick field you really have superconducting state, and for thin field you have insulating state. So you really have this superconducting with insulator transition. So this picture is probably most famous picture in the whole field of the superconducting insulator transition. That is the field. And my goal is kind of make something that is, to create something that is not to study and find whether we have the same phenomenon in one-dimensional superconductors. So, and there is interesting scaling theory related to the critical point in which you may rescale everything in such a way that you have symmetry between the superconducting and insulating side. And so this is actually more recent development for this field, and that is study of field of high temperature superconductor, also things called anion stones, so copper outside field. But what is interesting here is that doping is done not by the change is done not by changes the thickness of the field, by so-called electrostatic doping. So effectively people learn how to add carriers to the system. So, and again there is this scaling for this one. Well, nothing like that. There is no beautiful picture like that that exists for one-dimensional picture. So basically we have huge field to explore. In fact, field of one-dimensional superconductivity to some degree is confused. But before going to that, let me introduce a few things that we need just to have some discussion about one-dimensional superconductivity. So superconducting state is in general described by the quantity superconducting state of BCS superconductor is described by a quantity called order parameter. So here is this psi absolute value corresponds to basically concentration of superconducting electrodes. In a sense, and their exponent here corresponds to basically phase factor. So the physical superconductor is characterized by complex number. So in a sense, its motion of superconducting condensate is as equivalent to the motion of quantum mechanical particle. For example, current is proportional motion of this phase. And the other thing is that for superconductors, we may introduce a quantity called coherence length. There is actually several coherence lengths for superconductors, but for our discussion, what is important is this quantity Ginsburg-Landau coherence length. Basically, it has the following meaning. So let's say you have a superconductor and you try to suppress superconductivity at some point. So then, here you have, for example, entropy equal to 0, but then it sort of recovers, takes its own value at the distance that is approximately characterized by this parameter psi GL, this Landau coherence length. And that's length is very important when you basically define the dimensions of your superconductor. So when I'm talking about one-dimensional superconductor, I'm not talking about the chain of atoms. It's actually a quite sizable wire. It's still small in my case, but the size of the wire is smaller, should be smaller than this coherence length. So basically that means that if I suppress all the parameter, then over the whole cross section of my wire, all the parameter goes to 0. So it sort of does not depend on position within the cross section of the wire. It goes uniformly. So that's definition of one-dimensional superconductor. And from this definition, it's kind of clear that fluctuations are going to have a strong effect on one-dimensional superconductor. So if we suppress all the parameter at some point of the wire, it basically blocks the current. So we are going to get some resistance. So even though technically your system is in superconducting state, we still are actually detecting some resistance. There is more in this story, so in fact you cannot really simply suppress it. And the process of suppression is characterized by this quantum phase shift process. So basically, let's say you have a wire that carries a superconducting current. The order parameter is given by this number. This is constant quantity, and we don't have any current in your system. That just gives you the velocity of how wires goes through the system. So now let's say, as a result of thermal fluctuation, all the parameter in the system goes to 0 at some point along the wire. So basically, amplitude of all the parameter goes to 0, and if you still want to maintain the current, it has to be done by increasing of the gradient of phase. So basically, that means that you have more and more faster modulation of your phase at this point, and at some point what might happen is that your phase kind of unwind, lose this factor of 2 pi, and then bind together just to establish phase coherence support. So this process is called phase. So classically it was introduced by phase split, and basically there is kind of classical process of having this phase split in a wire. So there is a certain barrier associated with this process, and it's given by cross-section of the wire and phase coherence. So basically just the volume and HC squared gives you basically free energy difference between normal and superconducting state. So this gives you kind of activation of barrier for your phase split, and that is gives you a thermal-activated process. But in addition to that, people hypothesize that what you may have is some kind of quantum phase splits, when at low temperature, without actually having any borrowed any energy from surrounding, system may actually tunnel and form these phase splits. So basically, what happens if you have these phase splits is the following thing. So you have a system may actually gain 2 pi or release 2 pi in its phase. So what you have is a combination of voltage spikes with different polarities. And if you have a current in the system, then you have just a preferential number of the spikes in the voltage. So as a result, you have a resistance in your system. So that is semi-activated process. It's something that was known for a very long time. It was basically tested back in the 70s. But quantum phase splits are something that is really still controversial and really still not yet well defined. And the story of basically quantum phase splits were kind of brought to community by Giordano, and they were used to describe the following experience. But if you have semi-activated phase splits, then what you have is just exponential drop in your resistance that responds to basically more and more the growth of your potential barriers. But at low temperature, we detected these additional tails, and in fact, they could not be really explained by thermally-activated phase splits. So we proposed basically quantum mechanisms for them. And it seems like this tail-like behavior was detected in many other systems. For example, it was detected the small germanium nanowires in basically in carbon, but surprisingly in some other experiments, basically those experiments that I was part of was the postdoc in University of Illinois, they were absent. So basically what we have here is two competing systems. In one of them we have this proliferation of quantum phase slips, and in the other we have superconductor-insulator transition. So basically all wires that we have here can be separated into two basically into regions. So either superconducting or insulating. So just to maybe summarize the state of the field, I would say that we have basically two sets of experiments. So experiments by these dynamical manner, they must be done on short germanium nanowires, see superconducting-insulator transition. There is no these hot phase slips, but there is whole range of other experiments in which this strange phenomenon was actually observed. And if you look at this data, you notice that actually wires made of the same materials are here in both columns. So basically it's not really clear what is going on. And wires that were tested in Urbana were actually quite short. And later on I explained why it was like that. So there were some theories, I think it was developed that basically said, well, maybe long wires and short wires behave different. Maybe there is some sort of length-dependent physics that determines the behavior of this system. And there is a number of theory, basically talking about this field and discussing this field, and in particular, this later to specifically address this issue. So, for example, Evnikov said that because in so short and long wires are distinguishable because in short wires, when you have this process of phase slips, it's actually senses the presence of the backs. That somehow has a back action on the probability of your phase slip. And this theory basically tells you that in short wires you have enhanced interaction between the phase slips that actually also diminish this process. So in addition to that, there is a problem of phase diagram processes. So for example, what you see here, I am citing here two works, one on short nanowires and another actually on long nanowires. And in one case, basically everything is determined by resistance per square of the system. So that's kind of a specific resistance of the wire. This determines the system. The behavior of the system here is the total resistance of the wire.
How do you distinguish between short and long? What is the short wire?
Well, later on I show there is no length doesn't really matter.
But between these experiments, I mean, it's
it depends on kind of we need to go back to what they predict. So basically, let's see. So to have short nanowires, you need to have length that is larger than the coherence length, but your length also is smaller in this case than, well, when phase slip is happening, we have basically propagation of so-called short mode, that excitation of superconducting order wire. So basically the thing is that length of your nanowire has to be smaller than the typical length associated with this process, and length is given by this energy divided by temperature of this process. So basically it's related to length of propagation of short mode for the typical duration of the phase.
so it has a temperature dependence.
So for example, there is temperature dependence. Here, its length is determined, short is determined by this condition. So you're larger than coherence length, but smaller than coherence length divided by times square of channels in the system. Well, my message here is that theories can be dismissed. And that's actually irrelevant to what we use by the system. And the reason for that is, even though we have this large number of experiments, but you may look at this in two different ways. So one of the ways, yes, we really have this difference in behavior between long and short nanowires, but another thing is, well, all this QPS, all this process may be just artifacts of experiments. And in fact, these experiments are quite demanding. For example, let's say you have this tail here, and let's use it to wire is uniform, but this behavior can be easily mimicked if your wire is composed of the chain of superconducting grains. So then this decay will be due to the development of superconductivity in a single grain, and the tail is due to increasing joints of coupling between the grains. So really to do experimental nanowires, you have very strict sort of requirements for what you are making. If you do it wrong, everything goes to the boss. And this behavior, in fact, is known for the cases when these granular nanowires were intentionally made. So another thing that really can mimic this part, this behavior is if you do experiment in such a way that your system is not well protected from the noise. And that is basically, I would say, case of study that I experienced in Urbana. So we studied our measurements, we detected this tail that is shown basically in the red part. And then this is basically a picture of the lamp effect in Urbana, and experiments were done in this blue jewel. And we started to turn on and off all the equipment in the system, and we found that if we turn off this computer, then the tail disappears. So basically, screening and requirements for this ground loop controls is a strict process. So we have this two view, and my view is actually that this is part of the so basically, this is a list of questions that I kind of ask myself when I experiment with both. Are quantum phase strips real or artifacts of experiment? Is there any length scale separating critical behavior for short and long nanowires? Is there superconductor-insulator transition? Because if you have these quantum phase strips, what you have is really kind of crossover behavior. You never really have true superconductors. What is the effect of electrodes? What is the effect of dissipation? And so on. So basically, to do that, I needed to have minimum these three pieces of equipment. So I often kind of start to accelerate this one. So basically, I need to deposit wires. So I built this. We built this sputtering system. We purchased and assembled UX3 system, and I think most importantly, in 2009 we got this very nice electron microscope that allows us to really make very nice and nanowires that don't have this nice pigmentation. So before going to that, let me give you a few things about how wires were fabricated and studied in Urbana. So the method that was used there was called molecular templating technique. So basically, what we did, we basically placed a nanotube, carbon nanotube across a trench in silicon nitride and deposit material on top of this nanotube. So the device actually looked something like that, and wires were very nice, uniform, so there was no granularity. But big disadvantage of this method was that you cannot really make this device, you cannot really make wire long. So maximum that you can get is just about 300 nanometers. So strong desire here was actually to develop a technique that allows to be farther away from this field. So that's our intention to really use electron-beam disorder. So let me basically just tell you that we tried several things to make these wires. We had initially lots of problems with so-called lithography with positive electron-beam resistance. So later on we switch to something that actually works, and this is lithography negative. So let me explain how it's works. So basically you start with a substrate, and then you deposit your film. Then on top of your film you deposit so-called HSQ electron-beam resistor. You expose some portion of this resistor to electron beam, and then you develop, and basically everything that was not exposed to electron beam goes away, and you have this pillar of exposed features. And then you do the etching. So your cross-section area of the real sample actually looks something like that. Substrate, your sample, and you have this cap of HSQ resistor staying on top of this kind of curved individuals. And we really had, well, after some difficulties, but we have to skip this slide, we really got to very nice, we developed basically very nice combination. So the smallest piece of the device that we developed, I think it's close to record breaking, 5.8 nanometers. So we actually decided to go a little wider than that because we worried about some kind of non-uniformity of the figures. So that is one of the wires that was actually used for transport measurements. So what we see here is that it's really nice and uniform. Of course, big advantage of electron-beam lithography is that's lithography. You can actually print what you want. So that is
what is the tolerance time for
of 5 nanometers, but when you make it smaller, it's actually increases. So so that is our kind of standard pattern for making measurements. We have nanowire connected to electrodes. We have basically voltage and current probes. Or what we can do even more, nicer arrangement in which our voltage electrodes are made from nanowires themselves. So we can really touch the wire locally. So we can do 2-4 probe measurements. But we can do some other fancy stuff with this solution. So that is basically the main result of our study. So what is shown here is our resistance per length for a series of nanowires versus temperature. So for each wire in the bracket, I indicated the length of the wire. And what we can see that basically data goes mostly from superconducting to insulating, reduced, but there is no really dependence on length. They have appears as a random numbers. So basically, there is no length effect on superconductors. So the other thing to notice is that when we used amorphous moly-germanium alloy as a system, this is nice alloy in the sense that it has very short mean-free path. So basically, the resistivity of your sample does not depend on its size. That allows us to determine cross-sectional area, and basically that means that resistance in normal state, so basically here, is proportional to inverse of the area. So when we go up in the scale, we actually have wires with smaller and smaller cross-sectional area. And what's the tendency that we see here is basically wires with smaller cross-sectional area have smaller and smaller resistance. So basically the statement is that local physics, what you expect, cross-sectional area actually determines the state of your system. So what we have here is everything determined by local physics.
Question?
Yes.
So does surface scattering of the walls of your wire not contribute to
I think
resistance?
not. And well, it's amorphous alloy. It's basically scattering within it. It's already at this stage. So that's at least maybe it's but I the other thing, we actually in whole set of these measurements we did not really see this failed. So basically that means we don't really have any quantum physics, we have just nice superconducting crystalline transitions. So basically curves are getting broader here, but maybe that's something that needs to be inspected more carefully, because that's going to do some physics of the critical point. So that's I think our main statement here. We have superconducting slave transition. It's controlled by local physics. this actually there are no really length dependence.
So is this paper also on the same material?
No, it's different material, and I give it here as an example of what people usually consider as an example of crossover behavior at frequency. Just to illustrate that we don't really have this type of behavior. In addition to basically zero bias measures that I showed you before, we actually found that our wires have this zero bias anomaly. In fact, if we look here, so we have superconducting and insulating wires and transition from superconducting to insulating region. And zero bias behavior actually accompanied by transition from negative zero bias anomaly to positive zero bias anomaly. There is additional indications that we really have different behavior. So not everything actually is perfect as I mentioned. In fact, if we plot the data around this range of one combined graph, we actually see that they actually overlap. So that means that cross-sectional area is probably not the only parameter that controls the state of our system. So what I think is going on here is the following. So basically, for our superconducting wires, for example, this one again actually has nominal cross-section in which we have length equal to 6 and width and thickness equal to 6. So basically, cross-section of this lower insulating wire is kind of more extended, more entangled. So basically, it means there is kind of larger contribution of surface into the system. So probably that means that electron interaction is not as well screened in these flat wires. So probably in addition to the cross-sectional area, we have the second part of cross-sectional geometry also affecting our system. We also found that some of our wires can be characterized as so-called Anderson or localized superconductor. So what does it mean? So if you have one-dimensional metal, but what if you have a wire? So basically, Anderson localization theory and scattering theory tells us that all one particle states in this disordered wire are localized. And the wire is disordered. So basically, if your wire is thick, has large cross-section, then it may be really large localization lengths, but low temperature, well, theory predicts that all these electron states are localized. And one of the wire, if you look at this wire as it is a normal wire, do really have this localization length being actually smaller than the length of the wire itself. So basically, what we have here is a situation that if this wire is normal, if there is no superconductivity, this wire is going to be insulated at zero temperature. But what we have here is pairing between localized things. So basically, that what is constitutes this notion of localized superconductor is a concept that was introduced by So the other thing, so for each of our wire transitions abroad, but still may produce mean field critical temperature, or just taking it as the middle of the temperature. What we found that this mean field critical temperature actually drops exponentially this wire is inverse of the wire cross-sectional field. And we found this for two series of wires. So one of them is one constitution, basically a ratio of and the other is 50-50 composition of these two wires. So what is remarkable about this data is that if we extend the data to basically to infinite cross-sectional area, what we recover is critical temperatures that we expect for this bulk material. That is theoretically something that we expect from fermionic series, from series in which superconductivity is suppressed as a result of competition with this Coulomb repulsion. There is some theory related to that. We have tried to basically simulate this theory, try to repeat all these numerical formulas, and surprisingly what we found that the current theories, current thermodynamic theories, cannot really explain our data. Decay in our case is much stronger than what is expected from this I worried a bit that I made a mistake in this numerical computation, so actually what I did, I compared our data one by one to some other data, but the point here is that the theory was actually used to explain some data for amorphous lab nanowires. And let me just maybe wrap up saying that I just confirm what I said. Our decay in MoGe nanowires is much stronger than what you expect from this ferromagnetic series. So, in addition to driving superconducting insulator transmission by decreasing the size of the system, we can do it differently. We can basically apply magnetic field. That is a series of experiments that I showed you. So basically, what we have, we apply magnetic field, we start the superconducting wire, and then we just drive it into insulator. And again, as in the case of wires driven by cross-sectional area, we have transition accompanied by transition from in this zero bias data, accompanied by transition from negative to positive zero bias analysis. So there is actually clear similarity between these two superconducting insulator transitions, one driven by cross-sectional area and another driven by magnetic field. And expectation here, because of the similarity, that the same mechanism is actually responsible, or maybe similar mechanism is responsible for both processes. Yes?
Did you ever see negative magnetic resistance as Bob Dynes did in his?
No. I mean, I've seen it in Organa, but not with this one.
What is the direction of the field? The direction?
Direction of the field is not really so important, but it was applied not perpendicular to perpendicular. So, but effect of cross-sectional area is something that is still mysterious. Basically, we do not know what kind of mechanism is it. The dynamic theory that we saw explained actually did not work. But as far as the magnetic field is concerned, we actually know how to deal with this situation. So basically, if you have very thin superconducting wire, and if you place perpendicular magnetic field, there is no vortices basically entering the wire because it's really thin. But what you have is some kind of screening current, and screening current will basically increase kinetic energy of the electrons, or the group pairs that increases basically the energy of the system. And in addition to that, there is spin effect. Basically, the magnetic field tries to align spins of two. And both of these two processes are called pair breakers, and they basically destroy superconductors. We know parameters of our wires, we know what are dimensions of our wires, so we can actually predict what field is needed to completely suppress superconductivity in the system. And that's indeed what we basically found from this comparison. So critical field that we estimate from this theory well agree with what we get from the spin. And if we put these magnetic measurements into this general classification scheme, it will fall in a class of fermionic phase transitions, because the fact of magnetic field is in fact local. It suppresses amplitude of photophore. So
I'm sorry, once again, if you have a type 1 superconductor, does the critical field depend on the dimension? With no vortex, then
this is type 2.
This is type 2, but like lead, I mean, some of the data you showed us like lead.
Well, it depends. It depends on shape. It depends on size.
Let's say, I mean, pure, would it can? Because that would be the same mechanism.
It's not the same mechanism.
No, it's the same mechanism of suppression of superconductivity as it is involved. by breaking the pairs and basically trying to line up the spins.
No, it's the same mechanism in the sense that you don't have vortices in type 1 superconductor, you have superconducting currents.
No, I just have a general question. Does the difficulty drops in the nanowires in general? Or?
No, it's actually goes up. So that's actually surprising thing. That
Type 2 and type 1?
in type 2. I don't know what type 1. Basically, if you try to make another wire from type 1 superconductor, because you have so much scattering, you will have type 2 superconductor. So, but actually, it's quite amazing that magnetic field goes up. I mean, it's rather strange because it's just not much of the cross-sectional area. As you see, it actually depends on bits. The smaller the bits, the smaller the pair. And here, well, but that is sort of the same for bulk and for wires, but it depends on some. So let me kind of drop off and say basically what we found in this. So basically, we observed superconductor-insulator transition for driven by cross-sectional area and also by ratio of these to the thickness. And that was done for the first time in a long Nanowires. It was also the first observation of superconductor-insulator transition driven by magnetic field. We checked our system against arithmetic series. They didn't work. So apparently this needs to be reconsidered. So we did not see any quantum festivals. So likely experiment that observes that needs to be taken with some suspicions. So that is to transition parts. Sectional here, another one. I have some other stuff, but let me maybe this to be my last important. So basically there is some ongoing experiments that we are carrying out. One of them is just to look at the critical point, to figure out what is the origin of zero bias anomaly, to look at the separative effect. But what I would like actually to say is that, well, what we developed is essentially a new method, and it's very nice. It's like a microscope in INCC. You have very nice resolution, and you can really apply it to other materials, to other superconductors. But for example, you can make structures from graphene or other two-dimensional materials. You have your graphene layer, you have which is still open, you just lines out of that. That is something that we plan to do in the future. You have a really flexible tool because you can create really small structures. For example, here is 1 micrometer, it's 250 micrometers. You can create structures more complicated than just rectangle and some others. So another, my kind of real experiment is actually to look at quantum these phase slips and try to resolve them temporary as well events. And that is something that I hope to reach in collaboration with this IPRES companies that is located in Jersey. They're producing really fast superconducting phase slips. Okay, so let me skip some other stuff. And bring you to conclusion and conclusions. I have one more minute of protection. So basically, I put some efforts to make another slide, and it's almost kind of mysterious things that actually happened in giving up. So basically, what I show on the left is superconductor-insulator transition. So we apply magnetic field, we write our system of superconducting insulators. What I have on the right, I call it superconductor-insulator transition in organic light-emitting dyes. Because that's exactly the same behavior. So you have divergent negative behavior that goes into divergent positive. So basically, there is some mystics. If you want something really hard, it appears that it materializes, but sometimes not where you really want this. So thank you very much.
Techno is open for questions. Yes, please, Charlie.
You say that the insulator superconductor transition depends on possibly its shape, not just surface.
Yes, yeah.
Have you looked at grouping the different samples by the linear dimensions of the cross-section, like boundary interface length, or the non-boundary interface length, or I mean the non-substrate interface length, or just the overall length through, instead of the area? Have you tried to look at linear?
That is, we don't have much statistics.
Okay.
But that is exactly the approach is the project purpose. Change here is covered using schedules.
Okay,
So
cool.
maybe we'll give you an answer in a year.
I thought he was graduating before that.
Other questions? Yes, please.
So, if I, instead of applying magnetic field, can I achieve the same behavior by driving critical current, increasing currents as a wire? You do.
Critical current is more difficult in the systems because if you drive critical current, you have the process of so-called phase slip centers. So basically, phase slip center is when the section of your wire goes into the normal state, but that's not just normal. It's actually pulsates in time. It's kind of going back and forth between the superconductor and normal state. So that's really special area. We plan to do this experiment. I haven't tried this. Yeah, besides, the worry always is monogenerium is highly disordered material. If you drag it normal, it's lots of power generated in this area, so you don't have heating effects. So you need to figure out basically how to do it better.
Yes, please.
So you said that you enhanced the critical field of these superconductors by just going to lower dimensions.
Well, yes.
So how much? It's like, this is really surprising.
Well, it's not entirely true. It's just, let's say, let's look at the formula. So basically, the thing here is this orbital. So you have the piece here, right? Assuming, so basically, you have two processes. You decrease your diameter. TC goes down. But at the same time, kind of susceptance of your wire to magnetic field also goes down. So basically, whichever piece, you may get worse superconductivity, or you may get actually better superconductivity in terms of withstanding magnetic field. So basically, yeah, so let's, I think if you look at this formula, that is something that sort of tells you. Your DC0 goes down, but your pair breaker also goes down. So what happens to magnetic field, it depends on how these two parameters actually. Maybe there is some way of optimizing. For example, if you have really narrow wire like this way, maybe you gain something.
Any other questions? I have a basic question. Can you explain in layman language why the superconductor to insulator condition depends on the outline?
Whole theory different work.
I know, but in layman.
Well, let's say it looks like it's due to harmonic mechanism. So harmonic mechanism, what's the essence of it? So you have attractive interaction between electron and fluid and contract. But in addition to that, you have repulsion. You have repulsion between electrons. And this repulsion is getting stronger when you decrease the size of your resistor. So basically, part of the electrical field kind of goes outside of your wire. So they become stronger. So I think that's the essence of why the size of.
Any other question? If not, let's thank the speaker again. That was
they gonna hire you? Nice.
They actually did. They offered and accepted the position as vice president.
Really?
Well, I don't know if I can fully accept it.